actually see you guys. This is so cool, despite being across the screen. Happy Thursday, good to see you guys. Okay, couple things that I think will be useful for you to have nearby today. You see that I'm in front of my whiteboard today because we're going to do a good section of notes, probably half a page to a page-ish. And we're going to start there, so have your notebook ready to go. But we will also get to the point where we do some graphing. Not a whole lot, probably just 2 total set of axes. So we'll do a graph on number 3 and a graph on number 4. But you're also going to want a couple colors for when we get to the graphing. Because we're going to graph multiple graphs on one set of axes, and having the colors makes it so much easier to tell which one's which. And maybe you use colors for your notes too, however you want to get yourself organized. So let's do it. We really looked mainly yesterday at just the parent functions, just plain old sine, plain old cosine. Now we get into the good part of section 4.5, where we actually start getting to mess around with how these all look. Stretch them out, shrink them down, move them left, right, up and down, and play around. So, but in order to understand what we're going to do when we actually get to the graphing, I wanted to go over some of the behind the scenes action in terms of the way the equations are going to look, and get you some terminology that is really specific to just trig graphs when it comes to transformations. Now, transformations, you probably remember some of them from last year. I know we glanced over them in pre-calc a little bit, but I know algebra 2 is really where that all happens with, vertical shifts and horizontal stretches and compressions and all that kind of stuff. And we're going to use some slightly different terminology. It's going to mean the same thing. Okay. So in 4.5, it's graphs of sine and cosine. So I'm just going to call it graphs of sinusoids. And with the focus today being on, okay, how do we change the way these graphs look? What can we do to kind of mess with the way things look? Okay, and so I'm going to stick on this board, so eventually I'm going to erase some stuff and go back to it. But what I want to try to focus on today, if possible, is what these graphs look like when we write them as equations, and what we can kind of do with that. So trying to remember exactly how because I want to do the same thing that I did during study in kind of the same order. No worries, Riley. Okay, cool. So graphs of sine and cosine. Now, I am going to not worry so much about bouncing too much back and forth between using sine and cosine, because you remember from yesterday, they are the same graph, just kind of shifted one way or the other. But the thing that I know that I mentioned, certainly towards the end, but I want to make it really clear how important it is that although the waves look similar, the way that we write them, whether I decide to use sine in my equation or I decide to use cosine in my equation, or they give me one or the other and I'm supposed to graph it, is where we start. Okay, where the starting point is for a sine graph compared to a cosine graph, and how that will affect, you'll see eventually, how that will affect how we write the equation or how we graph it. Okay, super, super important. I know I said it yesterday, but this is how important it is. I'm going to say it again. Okay, sine, and I'm writing the whole word S-I-N-E, starts in the middle of the graph, and so I'm going to call that at the midline. Right? If I draw a little wave over here, right, there is a line, an imaginary line that cuts right through the center. And we'll talk about that midline in a little bit. But our sine graphs, if you remember, started kind of at the beginning and then went up from there. Starts at the midline and goes up. And of course, I mean from left to right, because that's how we're always going to read these graphs. But you'll notice that there are a lot of possibilities for where that starting point could be. It could be right here. Start the midline and go up. Start the midline and go up. Start the midline and go up. We just get to pick whichever one we want. Okay, and we'll probably pick the one usually just closest to the origin. Just make our lives a whole lot easier wherever that happens to be, right? And you can see that between these starting points, like if I get rid of this and I cover up the rest of that, like there's one perfect full cycle of sine, okay? Sine starts at the midline and goes up. And let me know if the pens I'm using aren't bright enough or something. I'm gonna order a bunch more things. Cosine starts at a, because it could be any maximum. Cosine is gonna start up here at the top, right at the top, right there. And you can see between those black dots, if you can see that close enough, between those black dots is one full cycle of cosine, and it's the same graph, but they're just shifted one way or the other, okay? And that's gonna come in really handy for us when we do eventually make our way to the graphs and we start graphing some transformations of these. But also, and you're gonna see that as the next week goes on, we start actually graphing them less, and we start analyzing them more. Like, here's a graph, tell me what equation could work. Or let's describe some of the characteristics of how this graph is different than just plain old sine or plain old cosine, okay? And so what I'm gonna do now is give you the general form of transformations of sinusoids, okay? I just love that word so much. Now, I am going to use sine as the function that I'm choosing, but replace sine with cosine whenever you want, and just this is the only thing that we have to worry about. That's the only change that ever gets made, okay? So I know I'm gonna use sine in this general form that I'm gonna give you, but go ahead and replace it with cosine. It's still gonna be a great form that you can use. The thing that makes these a little bit trickier in terms of writing the general form or writing these equations or just looking at a given equation is that sometimes they'll write it in a really nice way where all of the information that I would need is staring me right in the face. Sometimes there's some hiddenness to it, and I'm gonna show you that here in a second. So when I write these, I'm gonna write two equations. They're gonna mean the same thing. And I'm gonna start with the one that's not quite as nice as the second one, and I'll show you why here in a second. Once I write the two versions, I'll explain the difference between them. And then I'm gonna leave up the nice one, okay? Because that's the one that we hope to see most of the time. But if we ever encounter the one before that, I'll show you what to do. Okay, and that'll probably come tomorrow or Monday or Tuesday or something. Cool, so here we go. The general form of sinusoidal transformations. There we go. I'm gonna call it F. F of beta. Okay, and what I'm gonna do is I'm just gonna write it out, okay, with all of the letters. So no numbers in there just yet. I'll show you the better version, and then I'll keep the better version, and I'll erase everything else, and then we'll talk about what all these letters actually mean. But you're gonna recognize that this is gonna be vertical stretches and compressions, and horizontal stretches and compressions, and horizontal shifts, and vertical shifts, all that stuff from algebra 2. Okay, I'm just gonna use some pretty specific letters, and we'll talk about what those mean. Here we go. Okay, f of theta equals a times. Okay, now I'm picking a sine function rather than a cosine one, doesn't matter. Either one works. Sine of, okay, there's that vertical stretch or compression. There's the reflection if you wanted it to be. If you remember some of these things, yay. If not, no big deal. It's okay. We're going to work through them, I promise. Okay, so there's the vertical one. Here comes some horizontal stuff because I'm inside parentheses messing with our independent variable, which is going to be theta. But I could do two things, right? I could multiply by a number or I could add or subtract something. So you're going to see two things happening here. I'm going to have a b theta. Now, it's b times theta. Put the little dot there if you like. And then I'm going to put a minus sign instead of a plus sign because horizontal shifts are backwards than you might expect. Okay, I'm going to use the letter C as that kind of placeholder for us for that unknown constant. So remember, things are going to happen backwards. So if it's subtraction, like for me, subtraction feels like I should be going left. So where am I actually going to go? I'm actually going to go right. Okay, that'll come back to you, and we'll look at it, I promise. And then a little plus D at the end here for the vertical shift. Now, don't put those transformation names down yet, because I'm going to give you some slightly different terminology that applies just a trick. But here's the problem with this version of the general form. When we think about like transforming a parabola, well, when I decide to make that change, it's only happening to one function. Like here it is. There's no repetition. It's just I'm going to slide it left or right or up or down. I'm going to stretch it out. I'm going to compress it down. I'm going to flip it upside down. Whatever happens, there's kind of a middle, right? There's a beginning. There's a vertex. There's a place where the function has a center, if you will, okay? There is no middle. There is no center. These are infinitely long waves that just repeat, 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 repeat. And if I look inside here and I focus on the horizontal transformation of all of this, what happens when we start messing with both, changing the location of, like, let's say a starting point for sine, but also then taking that function and shrinking it down and maybe making the wave look like more like this, right? Making the waves happen faster, or maybe even stretching them out so it takes longer to get through them. What happens here is that the order matters a lot more than it ever has for us when it comes to transformations. Because of this periodic nature, this cyclical repeat, repeat, repeat of the same wave forever in both directions. And so the problem with what's written here is that this C is actually misleading. This is not the horizontal transformation, the horizontal shift that we hoped it would be. Because think about what would happen if I plug in a theta and I do it in here. What would happen is the horizontal stretch or compression, the accordion, because think about just like I'm going to accordion this thing down or stretch it out. The accordion nature of that would happen first here, and then I would shift it to wherever I wanted to make that starting point happen. But it's a starting point for a reason. That point has to get moved first, so it's the beginning of the wave. It's like we want to create a center. We want to create a beginning. I know that there really isn't one, but if we're going to graph these, if we're going to understand the location of like where this wave is happening, it's so nice to have a starting point. So what we're going to do, and it actually works out mathematically as well, that this does not work out the way we would love it to. We want to create the starting point, the location of a starting point first, because we can find one. I know that sine starts at the midline and goes up, and that cosine starts at a maximum. And if I can pick a starting point and like say, okay, there's the center of my accordion, and I can just go in or out from there, everything will be adjusted the way that I want. So let's create an equation where order of operations allows us to focus on adding or subtracting a number from theta first, and then doing the accordion of messing around with a horizontal stretch or compression second. In other words, let's bury theta minus something inside its own set of parentheses on the inside, because that will say, oh, well, order of operations says I got to do the inside of parentheses before I do anything else. So still f of theta because it's the same function. Nothing else besides the inside here is going to change. But this isn't what I want. This is what we want. What I want to do is I want to factor B out from the inside and focus on what would happen to theta with addition and subtraction first. Does that make sense? I'm looking at you guys now. Give me like a thumbs up if like the thought process kind of clicks for you guys. If you have questions now, now's the time to do it. Okay, cool. So what I want to do is properly factor out B from both B theta and from negative C. Well, B theta, take out a B, yay, awesome, perfect, just theta. That's all I wanted. I wanted to get to the point where I just had theta plus something or theta minus something on the inside, okay? Now, what is that going to be? Theta minus, okay, we'll stick with the minus. Well, this doesn't have a B. And so when I factor out something that does have a B, yay, it just disappears. But when I factor out a B from something that doesn't have a B, well, how am I going to write the correct version of whatever that constant's going to be so that if I did multiply that B back in, it would disappear? Well, factoring is just the opposite of distribution, right? Distribution is multiplication. Well, if I'm doing the opposite of multiplying, we're dividing. And what I'm going to do instead, in this black version, instead of just having C, we're going to have C over B. And that is going to be the correct horizontal shift of the starting point. And that's the one that matters. Because now think about like multiplying B back in. If we had to get back to this version, okay, B times theta, sweet, B theta, and then B times C over B, the B's would cancel and we just have C and life is good, okay? A little plus D at the end there and we're happy. Cool? This is the one we like. The one in black is the one that we like. But what's gonna happen is a lot of times, well, not a lot of times, but enough times, they're going to write equations like this. B theta minus C without the added set of those inside parentheses. See, I had like open, so I had to close there at the end there in black. They're gonna write it like this. It's up to us to factor out B if we wanna properly see that horizontal shift. Cool, all right. Now, let's talk about A, B, C over B, and D. And again, so minus, so switch signs when we're actually talking about the shift, because it's gonna happen in the opposite direction. Let's talk about what those mean, some names for what we're gonna give them, and what that means graphically when we actually get our hands dirty and start doing it. So I'm going to leave up this black equation. I'm going to erase everything else so we have something that we can use to judge with. Cool? Yay, sweet, all right, let's do it. Away it goes. I do like those like little waves up there. I'll probably keep drawing those waves so you can see something that goes with it. Okay, cool. Here we go. Now, all of these new words that I'm about to tell you all mean what you think they do in terms of vertical stretches and shifts and horizontal whatevers, okay? But there's some new words just because it's tricky. Here we go. A, of course, is the vertical stretch or compression. It's the reflection. Whatever goes out there, that's what it's going to do. But we give it a name because of what it looks like on the graph and also what its applications are outside of just plain old looking at math stuff. It's called the amplitude. A-M-P-L-I-T-U-D-E, the amplitude. Okay, and when you think about that word, maybe some of us that maybe are more musically inclined might see the word amp in there and think amplifier, like plugging an electric guitar into an amplifier and adjusting the volume, right? You're changing how loud the sound is. And that's actually what's happening. Remember, sound moves in waves, right? And so if I have a sound wave moving through space, what's happening is that when we adjust the amplitude, we are changing one part of that wave. And what that is the distance, and so it's always positive. So if it's negative, you just absolutely valid, right? The distance from the midline, we talked about that, the distance from the midline to an extremum. The distance from a midline to either a minimum or a maximum. So what I mean is, let me just draw this a little bit nicer. Right? We've got this midline that cuts through the middle. Okay? The distance from the midline either up to a maximum, like that's A, or down to a minimum, that's also A, because we're just talking about distance. And when you change that distance and you make either the wave taller or shorter, you are changing the volume of the sound that's moving through that wave. Okay? Because the higher the wave that hits your eardrum, the louder it seems to your ears. Okay? So it's really the distance from the midline to an extremum. Doesn't matter which one, just pick one, measure it, that's how far it's gonna go. And all we're really doing is just multiplying by a number. So like 1 sine of theta, just plain old sine of theta, that distance is 1, which kind of makes sense because if you look at a sine graph, we start at 0, we go up to 1. Or we start at 0 and we go down to -1. But if we had something like 2 sine of theta, okay, we'll start at 0 and we'll go up to 2. Or we'll start at 0 and we'll go down to -2, that distance. So not the full distance top to bottom, it's actually half of that, right? The distance from the midline to an extremum. That's what A is gonna do. Amplitude A, easy to remember. Okay, cool. B, right here, and of course the one right before it too, okay? That's your horizontal stretch of compression. That's your accordion nature of kind of messing with how quickly the graph goes up and down. So something like sine of 2 theta. Not 2 sine of theta, but actually changing the number inside that's being multiplied through that angle. What that's going to do is it's going to accordion, like I said, this thing either going to make it happen faster or make it happen slower. And what we see is that like between here and here, when we look at just one full cycle of, let's say sine, it's just easier to look at sine. What you've got in there is like one full cycle within a normal, what's called period. From here to here, that distance is called the period of the trig function, okay? How long it takes to, so this is period, to complete one full cycle, okay? What B does is it messes with that period, okay? And what we see when we mess with that, when we start messing around with B, is it changes how many full cycles we see, okay? So it's actually called, B itself is called the frequency. How many full cycles we would see appear within that normal period, okay? Frequency. How many full cycles, and when I talk about cycle, I just mean like one trip around through that one full cycle of that wave. Okay, how many full cycles we see within the normal period of whatever trig function we're dealing with. How many full cycles, and that's why it's called frequency, because we're just counting how many of them there are within that normal period. Now, when we're talking about sine and cosine, when we think about how long it takes to go through one full wave before it starts repeating itself, the normal period for sine and cosine is 2 pi. Right, that's how long it takes, because that's just one trip around the circle. Right? That's how long it takes to see that wave complete its full cycle. okay? When we change b, we are changing how many times that happens, okay? And so if I were to do something like sine of 2 pi, right? Sorry, of 2 theta, excuse me. The sine of 2 theta. Then what that means, I'll write it down, sine of 2 theta. Let's say we were looking at the function y equals sine of 2 theta. Our frequency is 2, which means I am going to see 2 full cycles of sine happen within that normal period of 2 pi. And if this is my regular sine graph, what would happen with sine of 2 pi, 2 theta, I keep saying 2 pi, gosh, is I would see a graph that looks like this, that I would be able to get through 2 full cycles within that normal period. Okay, and obviously that then changes what the new period would be. I'm gonna come over here, just in kind of a small space right here. Because b is not the period of the function. It's the frequency within the normal period. And what we're going to want to be able to do is figure out, all right, well, if a period is how long it takes to complete 1 full cycle, well, if I'm going to mess with how many times I see the trig function go through its wave, well, what I'm going to have potentially is a new period for my transformed function. And what would be really nice is if we could figure out a way to come up with an easy formula using b to get us our new period, okay? So think about it. If our normal period is 2 pi, there it is in black. But now I just went through a full cycle twice, okay? Well then, how long does it take me to complete 1 full cycle in this function? I'd love to hear from you guys if you've got any ideas. If 2 pi is a regular one, and I can do it twice because I have sine of 2 theta, what's my new period for this transformed function?
1 pi.
1 pi, right? It only takes me a distance of pi radians to make it all the way through. And so what could we do? I'm going to put an equal sign here for a second. I'm going to put a Greek letter over here in just a second. What could we do to our normal period of 2 pi using our frequency to get that new period of just 1 pi?
Divide by 2.
Yes, divide by the frequency. Divide by 2. Right? And so if we had something like sine of 4 pi, y equals sine of, somebody give me the overrun on how many times I'm going to say pi instead of theta. If we say sine of 4 theta, what that tells me is I've got a frequency of 4, which means I'm going to be able to get through 4 full cycles. 1, 2, 3, 4 full cycles of sine within my normal period of 2 pi. What would our new period be if our frequency is 4?
1/2 pi.
Take 2 pi, divide it by 4, divide it by your frequency. 2 pi divided by 4 would be pi over 2. And the symbol that we use for period of a trigonometric function is the lowercase Greek letter omega, which looks like a W whose ends are curved in at the top. Okay, there's omega, Greek letter omega. Okay, so omega is your new period, 2 pi over b. So while knowing that b is the frequency is really nice, what's really most important about that, super nice and helpful, is really to be able to just say, you know what, if I could just take my normal period, which for sine and cosine is 2 pi, other functions are different, potentially, we'll talk about those. Just take that normal period, divide by b, and we're good to go. Okay, cool. So B is your frequency. Your period is 2 pi over. Good. Okay. Now I'm going to talk about C over B, not C, because C is misleading. We have to use this version if we want to do that horizontal shift. But because we're talking about something that repeats, we use the phrase phase shifts instead. Okay, because we're just looking at one phase of something, and really we're trying to figure out where that starting point is going to be. Where sine starts, the midline goes up. I want to place that point where it should be, and then I'll just let the wave happen in both directions. Okay, so it is a horizontal shift of your starting point. I'll write that. I kind of like that. Horizontal shift of the starting point. But what you have to remember is that it's the opposite sign, right? Minus C over B, I'm talking about C over B. Okay? Things are going to go in the opposite direction than we would expect. Okay? Because if I can place my starting point and then worry about the period, I can place a starting point and an ending point and fill in the space in between. Okay? Because what we want to be able to do with graphs is try to complete at least one full cycle, and then, like we did yesterday, we can just copy it over. And copy it over in whatever directions we want, because these things go on and on and on and on forever. Okay, good. A is amplitude. I'm going to slow down for a second. Woo, we're doing good though. A is amplitude, distance between the midline and the top, or the midline and the bottom, which changes the sound of what you're looking at. Frequency is how many times we're going to see one full cycle. When you think about frequency, I don't know if radio rings a bell. When we talk about frequency, when you change the dial on your radio, what you are doing is you are changing the trig, the sine wave of that radio wave that your car is looking for. The antenna on your car searches for a specific frequency for a specific sine wave, because it changes a period. So, 1079 has a certain frequency, which means that that wave takes a certain length to go through its wave. And then you go to 93.3 and it changes something else, or 1075. And although small changes don't make a big difference on your dial, it makes a really big difference in which waves make it into your car stereo, which is so cool. Okay, cool. C over B being our phase shift, remember, going the opposite direction. And then D is the last thing, yay. That's going to be your vertical shift, right? That's what's going to take your whole graph and slide it up or slide it down. But what that really means for us, obviously every point's going to move, but what's most important for me is where the midline is. I want to know where the center of my graph is going to be, because then I can adjust the amplitude from there. I can adjust everything from the midline. I know where to start my points if I know where the middle is. And so I'm not going to say like D equals. What I like to do here is I like to say the line Y equals D. That's really what I care about, okay? That's going to be the midline. The line Y equals D is the midline. So when I graph these trig functions, I want to know where the middle is going to be, so I can do everything there. Okay, there you go. There's our really nice version of that sine or cosine. It doesn't matter. Pick whichever one you want. And here's all the details that go along with it. Okay, a lot of trig questions don't ask about frequency. They ask about omega. They ask for the new period of your function. So that's why this is starred twice and it's got two arrows. That's probably way more important than knowing, hey, what's the frequency? But knowing that that's what B is always. Cool. Questions? Doing okay? All right, let's actually do some graphing. Let's actually play around with this, but we're not going to mess around with like all four all at once. That's madness. That's too much. What we'll do instead is we'll focus on one of these four at a time. Now, we won't have enough time to do all four. I would like to try to do two of them. I want to mess with the amplitude, and I want to mess with phase shifts, which are two of the easier ones to change by hand, but also to recognize as we're working through going the other way, like here's a graph, give me the equation. What we're gonna do today is I'm gonna give us an equation, or two, or three, and then we are going to draw the changes that have happened to the parent function. So you can keep your notes nearby, but you want to take out that graph paper and a couple colors if you've got them. I would say having 3 total colors, maybe like a pencil and 2 others would be enough, or 3 colored pencils or whatever you're going to do. You're going to see me use 3 different colors because what we're going to do is we're going to draw 3 graphs on the same set of axes to really kind of magnify the changes and help you kind of see the differences, right? We're going to juxtapose those graphs so that they are more easily comparable, right? Juxtapose to put 2 things next to each other so we can compare them visually more easily. Okay, no calculators here. We don't need them. And if you want to have your old sine and cosine graphs from yesterday, that would help. But my suggestion, this is what I'm going to do most, if not every time, is when I draw, so this is like graph number 3. When I mess around with transforming functions and I'm asked to graph them, I always start by graphing the parent function on that set of axes first, because then I just make changes to individual points rather than in the entire graph. And we're at the point now, I made you graph so many points yesterday, we're at the point now where I'm only going to need 5 points from you for a full cycle, okay? Starting point, the end point, and then the 3 in between. Really, 0, pi over 2, pi, 3 pi over 2, and 2 pi, which is really nice because those are the only ones that are labeled on your axis. Spoiler, that's why I picked this set of graphs from the beginning, because when we graph these now and really moving forward, now if you want to put the 707s and the 866s in between, go for it. But when we start using amplitude and frequency and new periods, messing around with that can be really tricky. Here we go. So what I would like to do, sine's a little bit easier, so we'll start with that. I'm just going to call it y equals. We're going to do sine of theta here on this first graph, but because this one we're going to mess with amplitude, I'm going to change the distance from the midline up and down. I don't want to make the same scale that I used yesterday because eventually I'm going to go above where we were at. So I'm actually going to make every box worth 1 today, okay, both up and down. So 1, 2, 3, 4, and -1, -2, -3, -4. You are looking at a properly scaled graph. I don't have to put 1, 2, 3, 4, and -1, -2, -3, -4. I just have to tell you what one box is worth, or what some set of boxes is worth to do, okay? And then let's plot just 5 points, just the starting point, and then the ones that are labeled, and then we'll take that and we will copy it over, okay? Sine starts at the midline. How do I know that the midline is at 0? Because this is sine of theta plus 0. And y equals d is my midline, it's y equals 0. So I'm good to go, okay? I'm gonna skip pi over 4, that would be 0.707, don't need it. We're gonna save ourselves some trouble. We're gonna go to pi over 2, that happens at 1. Back to pi, which is 0. 3 pi over 2 at -1. And 2 pi, which is at 0. Okay, and I know that obviously this is squished down a whole lot more because of the scale that we use for y. It's okay, it's all good. Okay, and now I will take this and I will copy it over. Meaning my starting point over here at -2 pi was exactly the same starting point at 0. And I only mark off points on the axes whose x values are labeled. That's why I love these graphs, because then I don't get confused as to which ones I need to do to start. When I always graph my parent function first. And now I just connect them. Now be careful though, because I could very easily draw these with more straight lines than curves, but we know that these happen in waves. And so I gotta make sure that when I do this, I kind of get up to that line at 1 a little early and I flatten out and I curve and I get down to here a little early and I flatten out. I want to have that nice wave feeling, that curvature, to make me feel like I'm looking at a wave, not a bunch of straight lines. Okay, and yes, these go on forever, So we know that the arrows are there. I'm going to save us some trouble and some messiness. We're not going to use the arrows. We are good. We know they go on forever. We're smart enough to not have to worry about that. Cool. There it is. There's sine of theta. Okay. Let's change the amplitude, which means I'm going to change colors. Again, stop me if you need anything. I'm going to change colors here. And let's do 3. Ignore those stray marks. Sine of theta. Okay, y equals 3 sine of theta. Now, changing the amplitude does not change anything else. It doesn't change the location of midline. It does not change the location of your starting point for sine, because when you look at what that equation really looks like, your y values are 3 times bigger than they were for sine. And that's really how you can read that equation, is every y value now gets multiplied by 3. And what's nice is that because we've drawn the original parent function on this graph, now I don't have to start at 0. I can start over here on the left and just work my way to the right, taking every point that I plotted and multiplying the y value, in this case, by 3. Well, at negative 2 pi, the y value is 0. So 0 times 3, still 0. So I just put it down, same spot. We're gonna have some overlap, and that's okay. That's why we have different colors, right? And now, sure, all of these points in here should get multiplied by 3, but I'm not gonna mess around with that. I'm just gonna go to that maximum right there at negative 3 pi over 2, and I'm gonna take the y value, which is 1, I'm gonna multiply it by 3, and I'm gonna put a point up here at 3. And I'm just going to continue that throughout all 9 of the total points. Why 9 and not 10? Because this one is shared between both of those cycles. So 0, instead of 1, we're up at 3. Well, 0, still 0. Now negative 1 is down here at negative 3. 0, 3, 0, negative 3, 0. And then connect it. Again, smoothly, nice wave forming as best you can, not worrying so much about trying to be perfect, but I am gonna hit those points as best I can and try to be fairly symmetric and smooth. And stuff starts to look really cool really quickly. A lot of fun to play around with these kind of waves because you can make really cool designs. You can do them in your calculator too, and get different colors in your color calculator, and you just mess around with amplitudes and phase shifts, and you can make what look like 3-dimensional objects, which is really awesome. There you go. There's 3 sine of theta. Cool. Let's do one more. I'm gonna switch colors one more time. I'll go, I think the purple kind of showed up nice yesterday. I'll stick with the same thickness though. And let's make an amplitude of 1/2. Something that fits in this graph, but we'll have to do some estimating sometimes, right? There's no 1/2 line here. And I really didn't have a choice. If I had these 3 graphs ahead of time, if I knew that these were the 3 that I was going to do and I was on this graph, there's really no way for me to be able to get up to 3 and also have a perfect grid line at 1/2, just because we only have space for 4. Okay, but the process doesn't change. I'm gonna go left to right. I'm gonna take every y value, and in this case, I'm gonna go back to the blue graph. I always go back to the original and multiply by 1/2. 0 times 1/2, 0. 1 times 1/2, 1/2. Right? So I'm halfway between 0 and 1. 0, negative 1/2, 0, 1/2, 0, negative 1/2. And I connect from left to right, nice and smooth. So much fun. I love this so much. It looks so cool. I love it. There you go. There's what happens with amplitude. Okay. Good? Sweet. Hopefully you're feeling pretty good. I don't want it to necessarily be too easy. Like I feel like there's a lot going on over there. So being back here, I wanted to kind of give us a nice easy graphing experience to kind of end our in-person stuff for the week. I do have one more set of graphs we're going to do, so we'll go on to graph number 4 here in a second. But I'm not going to be able to get quite as far as I had planned last night as I was thinking about what I wanted to do, because I really wanted to make sure that the notes made sense. I really hope they did. If they didn't, stick around if you have questions. Happy to go over some stuff, which means I'm not exactly sure what I have in mind for you for tomorrow in terms of your work for the day. I want to get something into the grade book for sure for this week. Get you all your 100 to start off. You all deserve it. But I can't get too crazy with the graphing. I can't get super, super crazy with looking at equations. But I think that's the side of things that we might be able to do more with. Like, here's an equation. Don't necessarily graph it, but maybe. But just tell me about it. What's the amplitude? What's the frequency? What's the period? What's the phase shift? Stuff like that. Challenge you a little bit, but also make sure that it's doable based on the stuff that we've done so far. Cool. So I'm going to erase all this. You're going to move on to graph number 4, and we're going to mess with one other part of this. But I'm going to start again with the parent function. But let's pick cosine, because we haven't really done a whole lot with that today. Y equals cosine of, and that will be our first one. Now, because all I'm going to do with this graph, I'm not going to mess with amplitude at all. I'm not going to mess with the midline. We can go back to a scale where the grid line at the top is worth 1, because, hey, why not? We might as well maximize the space that we've got. It'll also give us more space to do our curvature too. When we were stuck in here, it was really kind of hard to make it look quite as wavy as we might like. So back to a scale up here with the 1, and that's enough markings on your y-axis to tell me what every box is worth. You could have gone down here and said 1/4 or 0.25. You could go here and say 1/2. You tell me what 1 box is worth or what 4 boxes is worth, or whatever. I'm good. You want to write in more numbers along your y-axis, go for it. But I am good right here. Sine started in the midline. Cosine starts at its maximum, okay? Our maximum for cosine is 1. And next week, we'll talk about domain and range and stuff like that, and what to expect with all different kinds of trig graphs, including sine, cosine. And again, I only need the marked off points along the way. So looking back at yesterday, we know that pi over 2 is 0, that pi is -1, 3 pi over 2 is 0, and 2 pi is 1. And yes, that looks very much like a V if we were to connect those with straight lines. So we have to be even more careful, I think, with cosine than we do with sine in terms of getting these graphs. But the great part about parent functions is I can take this and I can just copy it over to here. 1, 0, -1, 0, and then back up to 1. Okay. Again, graphing these correctly definitely starts with putting the right points on the graph, but how you connect them is going to make the difference. And if you really feel like you're doing the right thing. So when I connect cosine and I start at my maximum, I come out a little bit before I start to make my way down. And I get down to the bottom and I kind of flatten out here and I make sure I give myself some curvature at the bottom, and I get up here a little early and I turn the top and I do my best to make it. I don't want to connect things with straight lines, but I know that I'm not going to be perfect, right? I shoot for perfection, I fall short to excellence. And how could you be mad at that? Cool. We probably only have time to do 1. So let's just do 1 here, that's okay. Let's do 1 transformation of a phase shift. So cosine of theta, let's go like plus pi. Let's make that the change that we made. But what I highly, highly recommend that you do whenever you're dealing with phase shifts is you write them down. Like C over B equals, like what is that? Well, if it's plus pi, I don't have a B to factor out, yay, life is good. B is just 1, my frequency is just 1. Remember, I just have to change the sign, right? It's not pi, it's -pi, okay? But what that tells me is that that is the location of my starting point. I'm actually gonna add one quick thing to your notes before we go to. So I'm gonna make this one quick, and I'm gonna go back to my notes so we can add one last thing because I forgot to do it, which means, hey, there was my starting point. Well, now -pi is where my starting point is. That's it. And then I just go, and I copy, 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 knowing that the progression was 1, 0, -1, 0, 1. Okay, I just start over here. 1, 0, -1, 0, 1. And I just keep going. 1, 0, negative 1. I know that's the bell. Just give me like 30 seconds. I just keep it going. 1, 0, negative 1, 0, 1, 0, negative 1. And I ran out of space so I can stop. And now I work my way backwards. And what's so nice about working backwards, it's the same progression with cosine. 1, 0, negative 1, 0, 1. Okay, so at negative 3 pi over 2, I'm at 0. And at negative 2 pi, I'm down there. Really, you're just taking every point and you're sliding it to the left that far. If you want to just do 1 point, then you can just kind of follow that progression. If you want to do every point that far, that's cool too. And then I will connect with my nice wave. Oh, don't disappear. Although I can probably just keep going. Down. And then I go super, super fast so that you've got exactly what period 2 had. I want to give you a super quick breakdown, and then you can get out of here, of where your starting points are. If you've got a whole bunch, I know I'm making you dizzy, a whole bunch of transformations based on A's and B's and C's and all that stuff. So I got one last quick thing, super fast. Oh, I'm stuck. Don't get stuck. Okay, right at the bottom of your notes, I want to give you a starting point detail. Okay, starting point. Okay, and this is just based on phase shifts and amplitudes. Hopefully you can see me way down here. Okay. Okay, it depends on whether you've got sine or cosine. So if you're dealing with sine of theta, here is the location of your starting point. Remember, your C over B is where things begin. That's your starting point, and that's going to be true for cosine as well. C over B is where we're going to start, okay? The only thing that's different between sine and cosine, sine starts at the midline. Okay, cool. Where's my midline? It's right at D. That's where it is. I know exactly where that point is. With cosine, it starts at your maximum. Your maximum is a combination of two things: the location of your midline, and then the distance away from the midline to your maximum, right? And that's A. So the Y value of your starting point is A plus D. Done. Ta-da. Once you get those notes written down, so you've got them. I'm so glad I remembered. I almost forgot. You are good to go, okay? Check Canvas for tomorrow for a little bit of practice, and I will let you know what you need to do to take attendance. Probably like have a form or something like that, like we have in the past. And I will give you any updates that I have on anything else, but nothing live tomorrow. Enjoy your Friday. Have a great weekend. Shoot me a question if you have any. I know that there's a lot going on here, but we will have lots of time to work with it, to practice with it, to get better at it, and then we'll move on. Cool. So stick around if you need me for anything. Otherwise, have a great, great day, rest of your day. Have a good Friday. Have an awesome weekend. And I will see you live on Monday.
See ya. Thanks.
Thank you.
See ya.
Thank you.
Bye. You're welcome.